Just going to lecture a little bit, then we'll stop. And then just like we've done before, the exam will open up around lab time and you can take it during lab time and all that good stuff. Grab that. Okay, so what we're going to actually lecture on today is sort of a continuation. It's something we usually lecture on during lab time about balancing redox reactions. So I think it's probably a good time instead of studying something super fresh here before the exam. We're going to cover this, which is sort of an extension of what we were talking about last time, what we finished up talking about last time, which was basically redox reactions. So last time we talked about redox reactions, which are oxidation reduction reactions. We talked about how to identify what is being oxidized, what is being reduced, what's the oxidizing agent, the reducing agent. Also, we talked about oxidation numbers that helped us do that. So what we're going to talk about today is sort of how we go about balancing more complicated redox reactions. So the process and the steps to balance a more complicated redox reaction. And really the basis of what we're doing here is sort of what we talked about before. There's an oxidation half reaction, for example, where obviously the electrons are given off and it's on the product side of the reaction, which is why it's oxidation. And we also have a reduction half reaction where the electrons are on the reactant side and it adds to something, for example, and becomes something with a negative charge. So in a simple sort of half reactions, when you add them back together, as I think we talked about last time, you usually need to make sure that the electrons in each of the half reactions are the same. And you just basically multiply it by a common number if they're not to get everybody to the same. But when we balance more complicated sort of redox reactions, there's several steps that we want to follow. We want to basically first split the reaction into its half reactions. So you should end up with reactions like what we have above here. You should end up with an oxidation half reaction. And you should end up with a reduction half reaction. And once you sort of have split both of these guys up, the next thing you want to do is balance everybody, all elements other than oxygen and hydrogen. So we want to balance every other element that's there, just like we normally would with a coefficient, every element but oxygen and hydrogen. And once you've done that, then you want to balance oxygen. And we balance oxygen by adding water. And we add H2O to whichever side needs the oxygen. Now, when we do add H2O, we're not only adding oxygen, but we are adding 2 hydrogens. So to the opposite side that you add the water, you will add 2 H pluses for every water that's added. So one side will get the water to balance out the oxygens. The other side will get basically 2 H pluses to balance out the hydrogens that you added because you added water. At that point, you will add electrons to balance the charge in each half reaction. And then lastly, you will add both half reactions together. And if you do this sort of steps properly and sort of correctly, you will have a balanced redox equation, and it will be balanced basically 2 ways. It will be balanced just like a normal equation, which means you'll have the same number of elements on each side. And second, it will be balanced in terms of charge. So if you added up all the charge on the left-hand side of the arrow, it would equal the exact same number that you have on the right-hand side of the arrow. It does not have to equal 0 on both sides, but it will equal the exact same sort of charge on each side. So that's a lot of words. So let's go through one here together just to kind of show you how to put all this um, when you're balancing one of these. So let's say that we have this redox reaction, and let's say we are going to take iron plus some dichromate, and we're going to make iron 3 and some chromium 3. And let's say that we wanted to balance this in acidic conditions. So this is a typical sort of unbalanced redox reaction that you get. And again, here we're going to balance it in acidic. And later on, we'll talk about what does that mean and sort of what to do if it's not acidic conditions. But right now, we'll assume it's acidic. So the first thing that you really want to do is you want to split these guys off into two half reactions. One's going to be our oxidation half reaction. One's going to be your reduction half reaction. Now, you may not know which one is which at this point. So the easy thing to do is just to pick the two things that are kind of related to each other. So this is iron and this is iron, which means that should be one half reaction. And then obviously the other guy has some chromium in it, and that has chromium in it, and that would be our other half reaction. So these are splitting our reaction into the two half reactions, one again being an oxidation half reaction, one being a reduction half reaction. The way you could do that is look at oxidation numbers. So the iron here has a +2 oxidation number on the left. On the right-hand side, it has a +3 oxidation number. And if you were not sure, you remember we did sort of a number line. So in this particular case, we are going to the right and becoming more positive. And that means that this one is our oxidation half reaction. By default, that means that this guy down here should be our reduction half reaction. And again, here, you could actually figure it out. So we actually did this one at the very end, I think last time or near the end. It is +6, the oxidation number of our chromium. On the right-hand side, it is +3. Again, starting at +6, ending at +3, heading to the left there, becoming more negative, and going through reduction. So the first thing you want to do really is sort of identify what's going on, like I just did there, what's being oxidized, what's being reduced. We also want to kind of figure out our two half reactions. The next thing that we want to do is we want to balance these half reactions for all the elements other than oxygen or hydrogen. So in the case of the iron, there is one iron on both sides, so we don't have to worry about it. In the case of the chromium, that's, I think how you say that. There's two on the left, one on the right. So we just need to balance it like we would do a normal equation and just put a coefficient of 2 in front of it. And now we have balanced all the elements other than oxygen and hydrogen. So again, you just want to kind of go through and balance everybody like you would with a normal equation, put a coefficient over there and balance it up. Now, once you balance all the other elements besides oxygen and hydrogen, now you want to balance the oxygen. So we balance the oxygen by adding water. So in the first half reaction with the iron, there's no oxygen, so we don't have to worry about it. In the second half reaction, there are 7 oxygens on the left and none on the right. So to balance those 7 oxygens, we're going to put 7 waters there. Now, because we put 7 waters there, we also added some hydrogen, and that is 14 hydrogens. So we do need to put the 14 hydrogens to the other side here. And again, the purpose of putting those 14 hydrogens on the left-hand side is to balance the 14 hydrogens that we put on the right-hand side when we added the water. Any questions on that so far? So now that we've balanced all the elements, we balance oxygen, we balance hydrogen, what is left to do at this point is to go to each half reaction, and we want to balance the overall charge on both sides. So when I look at the top equation, the iron, I have a grand total of +2 on the left, grand total of +3 on the right. And the way that we could balance it is by adding electrons. So to the right-hand side, I'm going to add 1 electron. And the reason I did that is now when I add up the total charge on the left is +2, total charge on the right is +2. So we have now balanced out the charges on each side of the arrow in that first half reaction. And again, we do that by just adding electrons. We also want to do it for the bottom one as well. Now, over here, this is +14 positives. This entire dichromate has a -2 charge, which means overall we have a +12 happening on the left-hand side in terms of the charge. On the right-hand side, we got a grand total of +6. That means to balance out our charge, we need to add 6 electrons to the left-hand side. 6 electrons gives me a -6. So +12 and -6 is +12 on the left-hand side now. I'm sorry, +6 on the left-hand side and +6 on the right-hand side. So we're balanced there on their second one, +6 on both sides. Question on those steps there. Okay. We could also know that we did this correctly because if you remember, this top one was our oxidation half reaction. And when we write an oxidation half reaction, the electrons should always be on the product side, which they were. The bottom one was our reduction half reaction, and the electrons should always be on the reactant side, which they were as well. You should never, ever add electrons to the same side of the arrow because something is not right in that case. So they should always be on opposite sides, basically, of the arrow. Now we are ready basically to add both of those half reactions back together. Before we do that, we do have to make sure that we have the exact same number of electrons on each half reaction. And we don't in this case. So the bottom one has 6 electrons. Top one has only 1 electron. So what we need to do is multiply the entire top half reaction by 6. And that's going to give us the same number of electrons. So I'm just going to rewrite it on the bottom here. That's going to give me 6 of the iron 2s goes to 6 of the iron 3 and 6 electrons. On the bottom, I didn't really do anything with it, so I'm just going to recopy it. So 6 electrons plus 14 H pluses plus our Cr2O7 2 minus gives me 2 Cr3 plus and 7 H2O. Now that I have the same number of electrons on both sides, we could add both of these reactions back together. So when we add both of these reactions back together, everybody on the left-hand side of the arrow stays on the left. Everybody on the right-hand side stays on the right-hand side. And anything that's the same on opposite sides of the arrow will cancel out. So, for example, I'll just carry everything down first. So 6 of the iron 2 plus 6 electrons plus 14 H pluses plus Cr2O7 2 minus goes to 6 of our iron 3 plus 6 electrons plus 2 of the Cr3 plus and 7 H2O. You could think of the arrow as like an equal sign. So the electrons should cancel out, kind of like subtracting them to both sides. And at this point, there's really nothing else that's going to cancel out. And this will leave us our balanced redox reaction, our equation. And I'm just going to flip the page here since I don't have anywhere to write it. So that is, we'll go with 6 iron 2s. So we end up with 6 of these iron 2s plus 14 H pluses plus Cr2O7 On the other side, we are left with 6 iron 3s, 2 chromiums with a +3, I think, and 7 waters. Now, if we did everything correct and we look at this equation, and I copied it over correctly, we should be balanced both ways. And what I mean is if we just look at elements, iron, there is 6 on the left and 6 on the right. Hydrogen, there is 14 on the left and 14 on the right. Chromium, there's 2 on the left and 2 on the right. And oxygen is a 7. There are 7 on the left and 7 oxygens on the right. So it is balanced like a normal sort of equation. If we look at the overall charge that's happening, so if we add up the grand total of the charge on the left-hand side, we have +12 here, we have +14 here, and we have -2 here. So that is like +26 and -2. That's a grand total of +24 on the reactant side. On the product side, 6 times 3 is 18. We got +6, and there's +6, and +18 is +24 on the right-hand side of the arrow. So when you balance a redox reaction, it does need to be balanced both ways, both like a traditional equation, the exact same number of elements on each side, and the overall charge needs to be the exact same numbers on each side. Again, as you can see here, it doesn't have to be 0 on both sides, but it does need to equal the same overall charge on each side. This answer that I box up here would be the balanced equation in acidic conditions. So you put a box around what I did there on top, and that would give you your balanced redox reaction in acidic conditions. Now, we sometimes balance these guys not necessarily in acidic conditions, but sometimes we do need to balance them in basic conditions. And if we balance them in basic conditions, we do need to do one more step. So I'll put a little line here. So let's say we wanted to do this guy not in acidic conditions, but basically basic conditions. The good news is you can do exactly what we just did, which means basically you could balance this equation like it was acidic, get all the way to this equation. And then what you do is you need to add OH minus to both sides if it's basic condition. And the amount of OH minus that you add is equal to the number of H pluses there are. So once you balance your equation in acidic conditions, however many H pluses there are on one side, that's how much OH minus you would add to both sides. So again, here, I'm just going to recopy this down here. This was our balanced equation in acidic conditions. So what we're going to do now is if we were going to balance this in basic conditions, is once we've now balanced it in acidic conditions, we're going to see that on the left-hand side, we have 14 H pluses. That means that we will add 14 OH minuses to the left-hand side and also 14 OH minuses to the right-hand side. So in basic conditions, we add that OH minus to both sides. Now the side where we have H plus and OH minus, those guys come together to make water, H plus, OH minus. So if we do that and kind of condense some things down, this will give us 14 waters, which comes from the H plus and the OH minus. And our Cr2O72 minus gives us 6 irons, couple of chromiums, 7 waters, and our 14 OH minuses. Now at this point, what usually will happen is, as you can see, we have 7 waters on the right-hand side. They will cancel out and leave us 7 waters on the left-hand side. So again, you can kind of treat the arrow like an equal sign. You can kind of subtract those 7 waters off from the right to the left. And now that should leave us the balanced equation in basic conditions. And that would be 6 of our irons 2. We're left with 7 waters. We still have our dichromate. On the right-hand side, we have our 6 irons, our couple chromiums, and our 14 OH minuses. And again, if I did not screw up, it's a good chance, maybe I didn't, it will still be balanced in terms of the elements and also the charge. So there's 6 irons on the left, 6 on the right, hydrogens 14 on the left and 14 on the right. Oxygens, there are 7 in the first guy, 7 in the second. That seems like 14. There's also 14 on the right-hand side, and there are 2 chromiums on each side. And that means that everything is balanced in terms of elements. Overall charge on the left-hand side is, we have here, get some stuff out of the way so I can see it. We have plus 12 and 2 is like a plus 10 on the left-hand side. Right-hand side, we have plus 18 here. We got plus 6 here and minus 14 here. That's a lot of math there, but let's hopefully that's right there. That looks like a plus 10 that we're left with on that particular side, plus 24 and minus 14. So we are balanced again in both elements and charge on both sides. And this would be our basic balance equation. Any questions on those steps there? So there's a few different ways to do this, but probably the easiest way is like I just showed you in terms of the basic aspect of it, is to just do it for acidic conditions and then add the OH minus to both sides for basic if you need to do the basic one. You could add it earlier on, but there's a lot more canceling out that you typically have to do. Any questions on that one there? All right, so why don't you try one here to make sure. Let's say we had I minus plus MnO4 minus goes to, we'll go with I2 and MnO2, and let's do this in basic conditions. All right, so take a few minutes here and see what you come up with. Okay, so let's take a look and see how you're doing. I know you might not be done with it yet, but let's just take a look, make sure everybody's sort of progressing on the right page. All right, so we have again this redox reaction. We want to balance it in basic conditions. So again, you really can just do it in acidic conditions and then kind of do the basic part at the end, which is again, usually a pretty good idea to do. So to start off, we just one or two half reactions. So really just looking for, again, things that look like they're related to each other. So obviously I minus and I2 would be related. This has got Mn in it. This guy's got Mn in it. So those two probably should go together as well. Now, you can obviously figure out perhaps what is being oxidized, what is being reduced here. So oxidation state of our I minus is -1. Over here, I2 is in its natural state. So it has an oxidation state of 0. So again, if you kind of do the number line approach, we're starting at -1 and going towards 0. That means it's being oxidized if it goes to the right there, becoming more positive. So this would be our oxidation half reaction. While if we look at the Mn here, so oxygen is -2. There's 4 of them. That's 8. That's -8. And that means that the Mn in this case is actually +7. And if we look on the right-hand side, our oxygen is -2. That's -4. The Mn is +4 on the right-hand side. And again, we're starting at +7, ending at +4, going to the left-hand side there, becoming more negative, which means it's going through reduction. And by the way, if you could identify one, the other guy is the other thing in this particular case. Any questions on that part so far? Okay. Now, just like we talked about, we now want to balance all the other elements except for oxygen. So in the case of the iodine, we do need to put a 2 in front of the guy on the left since there's 2 on the right-hand side. In terms of the Mn, there is 1 on each side, so that is balanced. So we don't have to worry about that. Now that we've balanced the iodine, the next thing we want to do is look at oxygen. So since the first half reaction has no oxygen, you don't have to worry about it. Second half reaction, we have 4 oxygens on the left, 2 on the right. So remember to balance the oxygen, we add water. So the right-hand side here should get 2 waters. Those 2 waters will give us the correct number of oxygens on the right. Now, because I added 2 waters, I did add basically 4 hydrogens. So to make sure I'm not going to be short in terms of hydrogen, I need to add not 14. I still have that number from the last one. 4 would be a better number there. So we got 4 H pluses on the left-hand side, again, for the 4 that we added from our water. Any questions up to that point? So now that we've balanced everything, including oxygen and hydrogen, the next thing we want to do is add electrons. And we want to add electrons to balance the overall charge on each side. So again, looking at the left-hand side of the first half reaction, grand total of -2. Right-hand side, grand total of 0. So the right-hand side here will need 2 electrons. And that makes sense because, again, this is an oxidation half reaction. So our electrons should end up on the right-hand side. Looking at our bottom equation here, we have +4 here and -1 here. That gives us a grand total of +3 on the left-hand side. On the right-hand side, we have a grand total of 0. No charge happening anywhere there. That means that the left-hand side here will actually need 3 electrons. 3 electrons and +3 gives you a grand total of now of 0 on the left-hand side. Any questions on that so far? Okay, so we need to add both of these half reactions back together. But remember, before you could do that, the electrons in each half reaction does need to be the same number. So we have 2 in the top one, 3 in the bottom one. So 6 is a common number there. So the top half reaction needs to be multiplied by 3. The bottom half reaction here will need to be multiplied by 2. And that's going to give us 6 electrons in each of those half reactions. So I'm just going to rewrite it on the bottom there. So multiplying my 3 across the top guy, that is going to give me 6I minus goes to 3I2 plus 6 electrons. Multiplying my 2 to the bottom equation gives me 6 electrons plus 8 H pluses plus 2 MnO4 minus goes to 2 MnO2 plus 4 waters. At this point, now that we have the same number of electrons in each half reaction, we could add them together. If you want, you could cross out things here, or you could just bring everything down and cross them out. I'm going to cross them out here. So there's 6 electrons on the left-hand side of the arrow, and there's 6 electrons on the right-hand side of the arrow. And again, that should always happen. Those electrons should always completely cancel out. So you should not be left with any. And I think at that point, we are done. Nothing else will cancel out. So on the left-hand side here, we have 8 H pluses plus 2 MnO4 minus plus 6I minus. On the right-hand side, we have 3I2 plus 2 MnO2 and 4H2O. At this point, if I was balancing this equation for acidic conditions, I would be done. I basically put a box around it, and we hopefully should be correct. And if you just do a quick look at it, we have 8 hydrogens on each side, 2 MNs on each side, 8 oxygens on each side, and 6 iodides on each side. Grand total charge on the left is plus 8 and minus 8, which is 0, and 0 on the right. So again, if we were doing acidic conditions, we pretty much would just lay a box on it and we would be done. But since we are not doing acidic conditions, we have one more step here. And that step is we're going to add OH minus to both sides. And it's going to be equal to the amount of H plus that we have. So in this case, there's 8 H pluses. So we're going to add 8 OH minuses to both sides, not just one, but both sides. Again, the side where we have the OH and H plus will make 8 waters in this case, plus my 2 MnO4 minus, plus my 6 I minus gives me 3I2 plus 2 MnO2 plus 4 waters and 8 OH minuses. Now, usually always in this case, when you do the OH minus at the end, you will have some waters usually to clean up, plus some other things sometimes. So 4 waters on the right will reduce my waters to 4 on the left. And at that point, we should be balanced. So what I'll do, I think, is this move. Just kind of get some, clear it out real quick. So rewriting it up on top here, the balanced one that we're left with, we should now be left with a balanced equation. We should have 4 waters plus 2 MnO4 minus plus 6 I minus goes to 3I2 plus 2 MnO2 and 8 OH minus. Again here, we should have the same number of elements on each side, so still 8 hydrogens, also 12 oxygens on each side, 8 and 4. We have 2 MNs on both sides, 6 iodides on both sides. Overall charge on the left is -8. Overall charge on the right is -8. And it is balanced again, both ways that it should be balanced in acidic or basic conditions. By the way, we know this is basic conditions because we ended up with OH minus in the final reaction. just like before we added the water, the OHs here, we ended up with H plus. That's how we would have known that would have been acidic. So H plus will always show up in the end in acidic reactions when you're done balancing them. OH minus will always show up in basic conditions when you're done balancing them. Any questions on that particular one there? All right, let us let's do one more, and then that should be a sufficient warm up, I think, for the exam here. All right. So why don't you try this one here? Let's go with Cr2O7 2 minus plus C2O4 2 minus goes to Cr3 plus and CO2. And let's just do acidic conditions here. All right, take a few minutes or so, get started on it at least, and then we'll go through and see how you're doing. Okay, so let's take a look, see how we're doing here. Make sure we're at least on the right track. So same idea here. Just want to kind of pick the two things that are related to each other. So in this case here, again, we have our dichromate on one side, and we got some chromium-3 on the other side. And we have some oxalate, which basically has carbon and CO2. So those two guys also, again, related to each other. So we're going to balance everything other than oxygen and hydrogen here to start with. So on the first one here, it looks like we do need a 2 for our chromium. On the second one here, we have 2 carbons on the left and 1 on the right. So we actually need a 2 here as well, again, to balance out our carbons. At that point, we now want to move to oxygen. So our top one has 7 oxygens on the left, none on the right. So the top guy should get 7 waters there on the right. Because we added 7 waters, we are going to add our 14 H pluses to the left-hand side. On the bottom, we have 4 oxygens on the left. By actually balancing the carbon in this case, we ended up with 4 oxygens on the right, so it actually doesn't need any waters. We could also take a look and see what's happening in terms of oxidation and reduction. So the chromium here is +6 like we saw earlier, and +3. So again, going from +6 to +3, going to the left, becoming more negative. So this is actually our reduction half reaction. Now the carbon over here, that's 8 minus 8, and there's -2 left over. So that's going to be a +6. Actually, there's 3 of them. There's 2 of them. So +3 would be better than that. So +3 there gives us +6, and 8 is -2. And the carbon over here is going to be -2, and then that would be +4. So the carbon is going from +3 to +4, going to the right, which would be oxidation. Any questions on that? So now that we balanced everybody in terms of elements, we want to do charge. Overall charge here on the left on top, 14 positives, and -2 gives us a +12. Right hand side, we have +6 overall. So left hand side needs 6 electrons to balance that out. Also good because this is our reduction half reaction. So that's where we should be adding our electrons. Bottom, we have a grand total of -2 and 0 on this side. So bottom needs a couple of electrons. Also good because that is an oxidation half reaction, which means electrons should end up on the product side. So all that makes sense, and why it's good to really identify what's being oxidized and reduced. So when you do get to the part where you're adding electrons, you actually know what side they should go to before you add them, or you can verify that you did add them correctly. Any questions on that up to that point? So at this point, we are ready to add them together. We do need to get the same number of electrons. So since the top one has 2 and the bottom one there has, top one has 6, right? 6 and the bottom one has 3, or 2. We need to multiply the bottom by 3 in this case. So we're going to multiply this entire thing by 3. So I'm just going to rewrite these equations below it. So on the top, we didn't really do anything to it. So we just got this guy going like he was. On the bottom, we're going to multiply that 3 all the way across the equation. And now we can see that we do have the same number of electrons on opposite sides of the arrow, which is good. So we could do some reducing. So our electrons will cancel. And I think that will be it in terms of canceling. So everybody on the left-hand side of the arrow stays on the left-hand side. And everybody on the right-hand side of the arrow stays on the right-hand side of the arrow. And if I did not screw anything up here, this should again be balanced both ways that we've been talking about, which is both in terms of elements and also charge. So just quickly looking at it, it looks like we got 14 hydrogens on both sides. Got 2 chromiums on both sides. We have a lot of oxygens. I don't know, that's 12 and 7, 19, I think. So we got also 19 oxygens on the right-hand side, 6 carbons on both sides. Overall charge on the left-hand side is plus 14, and minus 6 is plus 8, and minus 2 is plus 6, and on the right-hand side, plus 6 as well. So balance, again, both ways, both in terms of elements and charge on both sides of the arrow. Again, the charge does not have to equal 0, but just needs to equal the same charge on both sides. Question on how to balance these more complicated redox type reactions. Any questions on any of that? Okay, we will stop there now. And a reminder, obviously, we are taking the exam at about 7:15. It should open. And normal sort of rules apply. You yourself take it, no notes, all those good things, no phone and friends or anything like that. So you make sure you take it with the proctorial. It'll be the same format as our previous exam. Again, there'll be the first part, which will be multiple choice, so you don't have to show any work for that. The second part, which is kind of the written part, will have certain questions where you do need to show the work. And then obviously you need to upload that, pretty immediately-ish after you submit it. Same, there'll be a module, so you have the honesty agreement, like all that good stuff. Take the quiz or the exam, and then upload your work, all found there. Also, the box there to drop your homework off in should be up there as well from the textbook, so make sure that you do upload that as well. And you'll have kind of like the same time as you had last time, so something like